Before joining SDSU, she earned her doctorate degree in data science from Worcester Polytechnic Institute. Her primary research focus revolves around the artificial intelligence and spatial-temporal data science with applications on smart city and urban intelligence. Today, Dr. Zhang will provide us with an insightful overview of her work, which centers on human behavior analysis using human-generated spatial-temporal data. She will discuss her research in imitation learning and its application in this field. Please let us give a warm welcome to Dr. Zhang.
Thank you, Professor Chen, for the introduction. So it's my great honor to share my research today. So the talk is about enabling urban intelligence by harnessing human-generated spatial-temporal data. So my broad research area is in urban intelligence, which is basically trying to provide smart services to serve people. For example, we have smart transportation with smart vehicle tracking, parking area management, and also autonomous vehicles. And we also have smart building, which tries to provide an integrated solution for air conditioning, lighting, and heating, and so on and so forth. And one more example is smart education, which is trying to provide interactive models to try to increase student engagement and interest. And more examples can be smart water management, smart energy management, and also smart healthcare. And given urban intelligence, I am particularly interested in this emerging field, which is human-centered urban intelligence. It is basically trying to empower urban intelligence by considering individual needs. But there's a question. You may want to ask, why do we care about individual needs? Why do the individual needs matter? So there are some examples. So as has been reported by CNN, the ride-hailing service providers like Uber and Lyft, they actually have provided very convenient ride-hailing services to serve people. However, oftentimes the drivers and also the passengers will choose to decline or cancel the orders. And this happens usually because the system assigned passenger orders do not match the individual preferences or the individual needs of the drivers. For example, some drivers may prefer long trip distances, and some drivers may prefer to serving in a certain area, for example, around the airport. So this makes this order cancellation happens. So it's important to consider the individual needs, the needs and preferences of the Uber drivers as well as passengers when trying to dispatch passenger orders to the drivers. And this is one example. So there's another example. So as has been reported by this Virginian pilot, during the opening years, the ridership of this new light rail line in Norfolk, Virginia was only half than expected during its initial operating years. And this happens because the individual preferences of daily commuters were not well considered during their transit planning. And this leads to a less usage of the rail line. So it is important to consider the individual needs when doing this transit planning and big strategies and the policies and also big constructions. Given this importance of individual needs, then where can we find the individual needs? So in urban areas, all these individual needs and individual decision preferences are actually embedded in their mobility and in their mobility data. For example, daily commuters will make a series of decisions on which transit mode to choose when they're commuting between their home location and their working places. And gig workers will also make a series of decisions on which customer to serve and in which order. And taxi drivers will also make a series of decisions like which direction to go, so that they are having a higher likelihood, a higher chance to pick up a passenger. And more example can be like personal vehicle driver, they will choose like a series of different routes to try to commute like to their destination. So within all these examples and more examples, like all these human like decisions are actually recorded like in the form of, for example, GPS trajectories. And we call this type of data that records human activity and mobility as human generated spatial temporal data, or in short, HSTD. So our research is like data driven. So we have been working with real world HSTD data sets. For example, we have been working with GPS trajectory data and transaction data from taxis, buses, subway trains, and ride-hailing services. And a bit more detail about the data sets that we were using. So we worked on data from over 20,000 taxis, 9,000 buses, and subway lines collected in 2014 to 2016. And our data from ride-hailing service providers are also accessible through our collaboration with Uber, their advanced technology group, as well as DDAI Lab. So given all this massive, huge human-generated spatial temporal data, we have two unique research challenges. The first challenge is, given this data, how can we learn and understand the unique decision-making strategies or this unique individual needs from this data? So how can we characterize and learn these individual needs and learn these individual decision strategies? And if for somehow we are able to learn these individual needs, the second challenge comes. How can we use the knowledge we have learned, the individual needs we have learned, to enable human-centered urban intelligence? Like, for example, some applications on transit planning, autonomous vehicle planning, as well as gig work dispatching. So surrounding these two challenges, being how to learn the individual needs, and the challenge two, which is how to enable human-centered urban intelligence, my research is an interdisciplinary research, basically circling around the spatial temporal data science and artificial intelligence with applications on smart cities and urban intelligence. And in each of the three fields, I have some like works. So in the spatial temporal data science, I try to leverage the HSTD data to try to make sense and understand human behaviors. And in artificial intelligence, I'm mainly working on imitational learning and also meta-learning approaches, and try to make some adjustments and modification and advancements on these AI techniques in terms of imitation learning, meta-learning. And I'm also leveraging diffusion models to try to improve the performance and design, make new designs of algorithm and improve the performance of meta-learning and imitation learning. And in the smart city application side, like I have works about like how to design like algorithms and applications for urban dynamics prediction, how to model the complicated interactions of multiple human agents, and how to design this decision-making planning for autonomous vehicles and their ride services. And in today's talk, I'm gonna circle around these two challenges. And so the outline about this talk is we are first gonna talk about the first challenge, which is how to learn the human decision strategies, where we propose the spatial temporal imitation learning solution framework. Okay, before talking about how to understand and learn this human decision strategies, the first question is, what are human decision strategies? So there is a definition over here. So it says the human decision strategies, it governs how a human agent make decisions as a policy in an environment to try to maximize some notion of reward. So what does that mean? For example, the taxi drivers will make a series of decisions. For example, at an intersection, if the taxi driver should turn left or turn right, and the taxi driver needs to make a decision and then try to maximize the likelihood or the chance of picking up a passenger. And for daily commuters, it will also make a series of decisions. For example, if I like taking a bus and if I'm taking a bus, like at which stop should I like get off? So they're also making a series of like decisions to try to get to their workplace or get to their home location as fast as possible. And in all these two examples, it is a policy function that controls how to choose a decision. And the reward function, it controls and evaluates how good a decision is. So the policy function and the reward function are actually the human decision strategy functions that we want to learn from HSCD. Then our problem for decision strategy learning naturally can be formulated like this, where here I'm taking this taxi passenger seeking process as an example. So in this passenger seeking process for taxi drivers, the taxi driver is making a series of decisions and doing like a series of actions to try to find and pick up a passenger. And in this process, the decision-related functions are the policy function and the reward function. So the policy function, it guides which action to take from the surrounding information. So the policy function will consider the surrounding information, for example, the surrounding traffic speed, traffic volume, travel demands, and etc. And embed this information as a state. And the policy will consider the current state information and then make an action or take an action. So this action are actually representing different decision choices. So if for the taxi driver at an intersection, there are a lot of decision options, for example, turning left and turning right or go straight forward, these are different actions. So for the policy function, it considers the current state information and tries to choose and output an action accordingly. However, for the reward function, it tries to evaluate the consequence of a decision at the current state. For example, the reward function will evaluate the current decision in terms of the state and action, and it will output score and evaluate how good the current decision is. And based on this taxi driver's individual needs and individual preferences, this reward function can reflect different factors. For example, income, and for example, the distance to the home location or the distance to a particular place of interest, for example, airports. So with this reward function, it will evaluate the consequence of the decision at the current state. And then our decision strategy learning problem can be defined as, okay, we are given a lot of input trajectories. Yes.
I mean, doesn't the policy have to consider things like objectives, like I want to go to the airport?
It's
Is
more
that embedded in this model? Something?
Yes, more like the reward function is more like a direct evaluation about the current decision, and the reward function, because when we are choosing an action, the policy function needs to choose an action that is able to maximize reward. So it's like separating this problem into two levels. There's a reward and there's a policy. Well, once we have defined the reward, then we want to choose a policy that is able to maximize our reward.
Okay. So you're saying that the policy seeking the reward is embedded in the policy. I mean, you sort of cast this as a probability of an action given a given state. But the action is always directed in some sense by the assumed reward or the objective. Right?
Yes, so it's like the actions are all like options we can choose. For example, turning left or turning right or go straight forward. And if our understanding, like in our evaluation system, like this reward, our reward is saying, I want like higher income. And there are a lot of travel demands if we are turning that, for example. In that sense, policy under the influence of reward will choose to turn left. So it's like the reward is like it's a general guidance. It is reflecting our like inner needs or like individual needs. But it's the policy that is telling us, okay, I have the needs, I have this objective, what action I should do.
Right, but I'm still confused because, I mean, there's this issue of objectives and, you know, turning left might be a sensible thing to do given the state, but it's not a sensible thing to do. The airport that you want to go to is left.
Yeah, so it really depends on the reward. So basically, once, yes, a human agent, for example, a taxi driver is chosen, the taxi driver's like individual needs is like has been known to us. So in that sense, the reward is fixed, a fixed thing. In that sense, there's only one optimal policy, or there's only one optimal action we can choose. Yes. So our problem is given the input as trajectories as sequences of state action pairs, and we want to learn the decision strategies in terms of a policy and reward. So it's more like if a human agent has been chosen, we want to learn the decision preferences and decision strategies of this particular human agent, this particular taxi driver. We have her trajectories, and then we want to learn this policy and the reward accordingly, based on the trajectory data. So, to solve this problem, we propose a spatial-temporal imitation learning solution framework, where we use deep learning models to try to model the policy and the reward functions. So, for each individual human agent or for each taxi driver, when we model her policy as a policy net and a reward as a reward net. Where for the policy net, it will input a state, it will take the state as an input, where the state will embed our surrounding information in the surrounding like area. For example, the traffic speed, traffic volume, and travel demands in the surrounding area. And it will output a probability distribution over all like potential actions. And for the reward function, it will take both the state and action as a decision as input, and it will output a scalar in the range of 0 to 1, with 0 indicating a bad decision and 1 indicating a good decision. So after this modeling of the policy and the reward, then the question comes, how have we jointly learned the reward and the policy? So in our spatial-temporal imitation learning framework, which is given, the general idea is given these trajectories, demonstrations from one driver, we want to learn the decision strategy, learn this policy as well as the reward, so that we can generate demonstrations similar to this particular taxi driver, or we want to match this demonstration trajectories. But how this matching can be done? So this is our reward neural network with input, state, and action, and output as a scalar. So when we are training this reward, we are like training a binary classifier. Its objective function is in this line, in the lower equation. So it is saying, okay, if for the current input state action pair is actually from a human agent, where pi e represents the policy from a human agent. If the current decision is from a human agent, we want this reward net to output a high score close to 1. But if otherwise, this state action pair is generated from our learner policy pi, we want this reward function to output a low score close to 0. So this is how we are gonna train this reward net. However, when we're training the policy net, we're trying to make this policy generate decisions similar to human decisions. In that sense, when we are trying to optimize the policy, we want the output action or the decision from this policy net to be able to get a high score from the reward net. So this red colored equation represents the objective function when we're training the policy net. So it's basically trying to minimize 1 minus R, which is basically trying to maximize the score obtained from this reward net. So, and also when we're training the policy net, we are having this H of pi term, which represents the entropy of the policy. In that sense, we are trying to make no more commitment other than trying to use this policy to generate human-like demonstrations. So in that sense, it's like the policy net, when during training, it's like the policy net and the reward net are like combating, they are like against each other, and it's like they are playing or min-max game. So their problem or objective can be formulated as a min-max problem. So after training, after the model is well trained and converged, we will finally reach a policy net and a reward net. We're using these two strategy functions, we are able to generate behaviors similar to this particular driver, similar to this particular human agent. So this is our spatial-temporal mediation learning framework. In terms of evaluation, so we evaluated our spatial-temporal mediation learning framework on real-world taxi GPS trajectory dataset. So within this dataset, which consists of sequences of GPS trajectories, where for each GPS record, it contains the latitude information, longitude, the current time step, and it also has an idle indicator, like saying if there's a passenger on board or not. And for baselines, we are mainly comparing with 4 linear models, including relative entropy inverse reinforcement learning, maximum entropy inverse reinforcement learning, apprenticeship learning, and also multinomial logic. And we also compared with this nonlinear model, which is based behavior cloning. So behavior cloning is a supervised learning approach where it's viewing the different states as input and viewing the different actions we can choose as different like labels or classes. So it's basically based on a supervised learning approach. And when evaluation, so from our large corpus of like drivers, we randomly select like 50 drivers. And for each driver, we have her trajectory data set. And we partition the trajectory data set as a training set so that we can train our models, and the testing set, which we can try to evaluate and generate the ground truth policies. And then we use the KL divergence to evaluate the difference between our learned policy and the ground truth policy. And the lower KL divergence will indicate a better model. So in this figure, the x-axis represents the 50 randomly selected drivers, and the y-axis represents the KL divergence. And our spatial-temporal mediation learning is actually able to attain the lowest KL divergence. Yes.
Is there a reason why you use that metric?
So it's basically because we are like comparing the ground truth policies and our learned policies. The policies we learn are like 2 distributions. So we are basically using KL divergence to evaluate the distance between the distributions. And other metrics can also be applied. For example, the Earth mover distance, the vector stand distance, or others. So basically, we actually use other metrics, but I'm only showing one over here.
Thank you.
Yeah.
Can you give a little more intuition about that? You have that entropy term, which is sort of like a regularizer.
Yeah, it's more like a regularizer. So basically, when we are learning the policies, so that we can generate like demonstrations similar to the like human behaviors. So in that sense, we can actually learn different, like a lot or like several policies that is able to generate similar behaviors, and they all are like human-like policies. But by adding in entropy, we want to like choose the one that has the minimal like bias. So even though we are having multiple choices, we want to choose one unique policy that is able to match our behavior the best. So we use the entropy term so that we can make this decision. It's great. Any more questions? Okay, so our approach is able to outperform our baselines. So this work has been published in ICDM 2019 and extended in ICDM 2020. So after talking about our spatial-temporal imitation learning solution framework to tackle the further challenge, there are actually a lot more practical and theoretical challenges for spatial-temporal imitation learning. For example, here is the spatial heterogeneity and sparsity challenge. So as you can see from this figure, all the colored areas are the trajectory coverage of one taxi driver in our data set. So using this taxi driver's trajectory, we partition her trajectory into those happening in the west part of the city and those happening in the east part of the city. And with these two portions of trajectories, like we are able to learn their decision-making preferences accordingly. So we can use the west trajectories to learn a west preference and use the east trajectory to learn east preference. And then we compare them. And we found out that these two preferences we learned do not match. And we also further learned that this phenomenon is not uncommon in our data set. That is, taxi drivers' decision-making strategies change across geographical regions. And also, obviously, from this figure, we can observe that one taxi driver's trajectory alone do not cover all areas of the city. So then this gives us the question: how can we learn the decision strategies of a target driver in unobserved regions from our data set? So our solution, our idea is, how about sharing knowledge across human agents and spatial regions so that we can use the crop knowledge to help us understand and predict the behavior of a target driver in an unobserved region. So we propose this conditional generative adversarial imitation learning approach, which is SIGIL. So we have introduced, based on the spatial-temporal imitation learning framework, we have introduced this condition latent, or the condition, where the condition includes two parts of information, which is driver information as well as the region information. So for the driver information, it will be some information related to the driver's home location, working schedule, and so on and so forth. And the region information will include information like the latitude and longitude range of this particular driver. So by having this condition, we input this condition into both the policy net and the reward net, where now we are able to learn a conditional policy and a conditional reward. So yes.
I mean, how do you make the decision that you were going to partition this problem according to geography, say, as opposed to time of day, like it's noon, the guy wants to go get lunch or something like that? Is it just intuition that that's something that you are seeing differences in how drivers behave?
Yeah, it's like so different information will actually affect different decision makings. So in our observation, we actually try to set it, okay, if there will be differences in the activities. So we just leveraging our data, we learn their preferences and we do the matching and find out, okay, it's actually.
But you have to partition and have to decide, well, it's the east side or the west side. And that's how we're going to partition the problem and look at how different the
Yes.
policies.
Yes, good question. So what we're trying to decide is more like the left side is like have some like unique geographical features, like it's more like the left side is having less like inhabitants or less like people living around there, and the like the left side, the east side is having less people like living around there, and the west side is having more people living around there. So basically, we are trying to make this partition, and we are trying to intuitively like decide based on this, and we are actually trying to get like an observation. We want to see if this preferences match, and if exists one partition that making these preferences doesn't match, and then this is our challenge. And also, so there's actually like a problem or it's like a research field in spatial temporal data science, which is a spatial heterogeneity. It's basically the characteristics on this like geographical like information that is leading to this problem. So we are just like using that example to show that actually this problem happens. This problem is there. Yes.
A bit confused. So are you trying to learn what action the drivers take based on the state, or whether the action was to do?
Both. So we learn both the policy and the reward. So we not only want to know what the next action is, but also want to know if the current like action is good or bad. So we want to learn both.
So what kind of reward are you considering?
The reward is actually learned using the demonstration data. So it's basically the reward is based on this human agent. It's not like predefined, it's learned from data. Okay, so I'll continue. So basically using condition, we are learning a conditional policy and a conditional reward. So the conditional policy will tell us, okay, for a specific taxi driver at a specific region, at a specific state, what action should I choose? And the reward will tell us for the specific taxi driver at a specific region, at a specific state, if the current decision is good or is bad. So with this condition term, we are able to combine and unify this policy and reward pairs from various human agents into one like model, into one pair of policy and reward. By tuning different conditions, we are basically tuning different drivers. So by introducing the condition, we are unifying and combining the models from various human agents. And during training, by familiarizing the policy and reward with various geographical features, as well as like decision-making styles and strategies, our model is able to share knowledge and learn location-dependent strategies accordingly. So this is our condition, our scale idea. By trying to leverage crowd knowledge to try to understand and make sense how a target driver will be making decisions at that location. Yes.
Generally, the model, are these models, I'm assuming they're just like regular opaque models, but was there some sort of like layer where you can kind of view these patterns?
Yeah, so basically we are proposing like a general like model. It's not like we need to be specific if this needs to be a fully connected layer or this needs to be a like using a CNN. Yeah, implementation, because as you can see, our like input is more like a feature map. So in that sense, we are more using the CNNs. And yes, so you're totally like your question is very good. So we are actually changing different architectures for the policy net and reward net. We are changing it to LSTM so that it can consider more historical information. We are changing it to transformer so it will be more like efficient. So it's basically this solution framework is like the general like neural network framework where we can replace this different neural networks in this policy net and reward net based on our needs. And there's actually another work, the trajectory scale work that I will mention briefly in the following slides is actually using the transformer to replace, or the attention decode, the transformer decoder to replace the policy and reward.
I see. And taking, well, even for this particular example, where you're using CNNs or
CNNs.
CNNs, were you able to look at, for example, the very last layer, look at the heat map, to figure out what behavior would be for another?
Yeah, like very good question. So actually, when we're training this model, I didn't look at the output or the heat map from the last layer, but there are like other works based on this work. So it's like a act scale, which is an explainable scale that is trying to understand and visualize the heat map from the final output there.
Thank you.
Welcome. Yes, I will continue. So basically, that is only the spatial heterogeneity and sparsity problem. So we have more practical challenges. For example, the temporal challenge where, as I have mentioned, that we have proposed trajectory scale so that we can consider the historical decisions. The historical decision, like how the historical decision is affecting the current events. And we also propose a net scale like model when we are having a low quality demonstrations from the drivers. And I also investigate this theoretical challenge for the GALE architecture where I propose this F-GALE is basically trying to change this training mechanism for GALE so that it can like perform better and more efficient. So this part are all about the spatial temporal imitation learning. How are we using spatial temporal imitation learning to make sense and understand how human agents are making decisions? And then I will come to our next challenge. After we learn all this knowledge, how can we enable human-centered urban intelligence applications? So to summarize, so for the downstream applications, I actually have some works that care about human-centered transit planning, where I have this DAC-ML framework trying to better visualize and understand the human activities and human mobilities and urban status. And I also have this IMAIL work, which is trying to consider and model this multi-agent interaction for gig work dispatching problems. And I further studied this human-centered autonomous vehicle planning problem that has been accepted recently, which is the one I'm gonna introduce. So, first of all, why do we care about human-centered autonomous vehicle planning? So with the technology in perception, planning, and decision like making, like proliferating, so it actually has made or realized the autonomous vehicles. So we can see a lot of prototypes running on the roads, for example, the Waymo, the TuSimple, and the Neural. And among a wide range of applications of autonomous vehicles, for example, the freight delivery, order fulfillment, farming machinery, and robotaxi, which is the self-driving ride-hailing services, or robotaxis is actually a very important application because it is able to provide equal services to anybody at any time and is able to help reduce road fatalities and try to provide more convenient services. So in this research, I would like to study how to design these passenger-seeking strategies for self-driving autonomous vehicles or for robotaxis. So I want to design a human-centered autonomous vehicle passenger-seeking strategy. But why? So the first why is, since I have been talking so much about like how to learn human strategies, and if we have taxi drivers, why not directly learn how taxi drivers are doing and then directly apply it to robotaxis? So here's one question about human decisions, which is human drivers do not necessarily prioritize serving passengers. For example, in this map, there are 3 drivers, driver A, B, and C. each of the drivers have her own decision-making preferences, and they have their own working comfort zones. For example, the driver B preferred to serve around this airport area. And it is because of like everybody has her own like individual preferences that leads to like an uneven distribution of services, which will lead to passengers on the bottom left corner feeling to be well served. So that is the reason why we cannot directly apply the strategies we learned from the human agents. So another question. So if I am like I care so much about like trying to prioritize like services, why not like design a reward that only prioritizes shortening seeking time or somehow equivalently shortening passenger waiting time? Okay, we can actually do that, but it will lead to safety issues. It will lead to reckless decisions and risky behaviors. So for example, in this map, all these gray colored regions are dangerous regions that we want to avoid. And suppose we are currently at this green grade, and there is a target which is a passenger waiting to be served in this brown grade. If we only prioritize shortening seeking time or shortening passenger waiting time, the action we are likely to choose are turning right. So basically this action. However, there is this dangerous region over here. And if we are only like trying to prioritize shortening seeking time, it will lead to us driving off the road. So it will lead to reckless and unsafe behaviors. So we still need human behavior, we still need human experience, so that like given all this human trajectory data, we can actually the human trajectory data are like the positive sample. They are telling us, okay, which actions are actually safe. So we somehow want to follow like human knowledge. However, we also have our prioritize in improving service quality. So our problem of human-centered autonomous vehicle passenger seeking is, okay, we are given a lot of trajectory data from diverse taxi drivers. We want to learn passenger seeking policy that is able to prioritize service quality and service safety. So instead of like human agents providing an even distribution of services, we want our autonomous vehicles to provide ride-hailing services that is able to cover the whole map, that is able to provide eco services to anybody at any time. So our solution is a conservative actor critique, and the general idea of our solution are we first of all using spatial-temporal imitation learning to try to estimate the trip demand from the taxi trajectory data. So basically, we're leveraging the reward that we have learned. And then we modify and synthesize the reward so that we can find a balance between trip demand and the decision safety with a conservative penalty. So the conservative penalty is saying we prefer conservative actions, we prefer conservative decisions. If we see from the like human trajectories, these actions, these decisions, human decisions are more likely to be safe. So we are more likely to follow how humans are acting. But we want to prioritize providing good, high service qualities. And using this synthesized reward, we can learn the policy based on the offline reinforcement learning. After learning the policy, we actually have like the action plan so that we can let these robot taxis to provide services to serve people. So in terms of evaluation, I'm also only showing like a little part of the evaluation. So we also use the GPS trajectory data. We have So this shows an evaluation example or case study around this shopping mall area. So in this figure A, all these passes in this grid cell represent one human agent's trajectory when seeking for a passenger. So it takes this particular human agent about 30 minutes to find and pick up a passenger with a trip fare at around $16. Using our say conservative actor critique strategy, we are able to quickly find a passenger to pick up within 5 minutes with a trip fare at around $15. And also at the same time, so here is a dangerous region. We are also able to learn conservative decisions and try to avoid dangerous and reckless behaviors. So with this, our CAC policy is able to prioritize a customer-centered or human-centered self-driving ride service quality. So after this, I'm gonna talk a little bit about my future directions. So one direction is, so as I have introduced, all the works that have introduced are mainly based on the analysis for individual taxi drivers, for individual human agents. However, in real world, human agents are not independent. They are actually living in an environment where there are a lot of other human agents. So in this example, in this figure, for food delivery workers and ride-hailing drivers, if they are serving in the same region, there will be multiple workers working together, whether they are collaborating with each other or they are competing with each other. So this interaction is as if they are playing a game. So then this research question comes, how can we model this complicated interactions of human agents? And then if we are able to model them, then how can we develop a multi-agent imitation learning algorithm? So this is one direction. So another direction is I want to leverage the proliferation of data, try to use this emerging multimodality data to provide opportunities and to try to bring urban intelligence to another level. For example, if accessible, we can leverage the CCTV footage or video data. We can leverage traffic regulation data, the weather forecast, as well as a roadmap to try to give a holistic and global information for urban intelligence and to bring urban intelligence to a more higher level. So currently, a lot of my research are based on transportation and urban planning. And in the future, I also look forward to opportunities to combine AI, apply AI to health and well-being energy and ecosystems so that I can contribute this good techniques in AI to local communities and also to industries and also local communities. So basically, to summarize, I have introduced the two challenges of enabling urban intelligence by harnessing human-generated spatial-temporal data, which is the first challenge where to try to understand and learn individual needs, we propose a spatial-temporal imitation learning framework so that we can learn this human decision strategies. And leveraging this human decision strategy, knowledge, we are able to design human-centered smart city applications. So that is pretty much of my research work. And if you have any questions, that will be great. And thank you. Yeah.
Now, one of your slides, you were conditioning your policy on the individual driver. I don't understand how that can be used in a general sense. I mean, you've got, 20 drivers and you end up basically with a different policy for each one. Do you have some method of averaging or synthesizing that information?
So basically,
with a more global.
Yes, basically, each driver, it has one pair of policy and a reward.
Right.
And so basically, we can see a driver A has a pair of policy A and the reward A, and driver B has a policy B and the reward B. So instead of having this this condition or this pairing, what we are doing is we are generating like a general policy net and a general reward net, where we view this different driver information as different conditions, or it's like it's just like different conditions. And if we fix the condition to be driver A, then the model needs to output the policy for driver A and the reward for driver A. So it's the conditions like the things that can tune which driver we are learning.
Okay, but that doesn't, I mean. So, I mean, you seem to be saying it's sort of a training tool. But I still don't know, I mean, it seems like you want something, you're assuming that human beings make good rational decisions, and you want some sort of, seems like you want some sort of global policy and reward structure based on some large sample of drivers or something, which will require combining that information.
It's actually like combining the information, because when we are training the policies and reward for each individual driver, we are only using this particular driver's trajectories. But when we are training this large model for various drivers, we are using all of their trajectories. And in that sense, we are familiarizing this model's policy and reward with all drivers' demonstrations. And then there will be somehow like global knowledge learned. And by changing the different conditions, we're changing to, okay, I want to switch to driver A, and this model needs to tell us what driver A looks like. Yes.
Well, I have a question. What kind of actions are you considering? Is it like going right and left, or going to a certain region or a certain street?
Yeah, good question. So basically, in most of my research, I'm using, as you can see from this. Yes, so as you can see, for most of my research, we are partitioning the map into grids. So the action for a particular driver, the driver that here, the actions are going to either of these 8 directions, like jumping to this neighboring grid, or jumping to this neighboring grid, or staying as the same grid. So this is one way of modeling how are we defining the actions. There are actually other ways of defining actions. It can be based on the road network. It can be, the action can be choosing to be on this particular road network, or choosing to turn out to another road network. So this is based on different modeling.
Because even, well, I was thinking maybe like a human taxi driver, right? But maybe that taxi driver thinks about a region close to maybe like a train station, or a region close to some important landmarks, right? In the city. I don't know. I guess it comes into the modeling.
Yes, and it also is related to the granularity of the problem. So in this case, we are talking about like each state has like a grid cell, but it can be of like more like different granularities. It can be the actions, or the states can be just the surrounding information, and the action is like I want to like change a lane, or just turn left or turn right. So that can be like a granularity. So there are also research around this area, and there are also like a more like global granularity, where people trying to say like to learn very general policy. For example, if the taxi driver prefers to go to the shopping mall region, or prefers to go to the airport region. So that is actually based on the modeling and the problem granularity.
And well, I forgot to say that the presentation was very interesting.
Thank you.
I thought you did a good job. I was thinking, let's say when you have these robot taxis, I think you call it, right? So the robotic taxis, to maximizing the waiting time for the customers, right?
Yeah.
So I guess you will also have to consider other factors like fuel efficiency, right?
Yeah.
Then I guess another another challenge in your research.
Yes, that's very good. Like that's a very good comment. So basically, we are like using this robot taxi only using the safety concern as well as the service quality as two like it's more like intuitive examples. It's more like for the service quality, it can actually encompass like various aspects. And for this, we are only considering this waiting time. We can also consider this like the fuel like usage or also the mileage that can also work. Like so we are like starting with this stage and trying to make this like problem more like compact.
Right.
Yes.
You showed data earlier on drivers and that KR metric. Was
Yeah.
that data from the test set or was that a validation set?
Yes. So the KL divergence is like a distance matrix. So it like try to evaluate the distance between our learned policy and the policy and the ground truth policy. So the ground truth policy are estimated like empirically estimated from the test site.
So in other words, when you were, those drivers were never a part of the training set?
Yeah.
Gotcha. Perfect, thank you.
Yeah. And more questions? Yes.
For the good and bad decision making, so are you using like a binary, like this decision is good or this decision is bad, or like, are you able to split it up into like, you know, a better decision, a worse decision, best, worst, things like that?
Yes, good question. So basically, currently, the spatial temporal imitation learning output is a scalar in the range of 0 to 1. So in that sense, a score closer to 0, like 0.1 is a bad decision, and a score closer to 1 or 0.9 is a good decision. And what you said is very like it's very good. It's like it's actually a very good comment. So there are also approaches where like the output from the reward function can be of high dimension of like multiple dimensions. For example, one dimension is evaluating if this current decision is good or bad, and there can be another dimension, for example, if the decision is from driver A or driver B. So it actually can be based on your problem, your like model output can be like also different. Thank you for the question. Yeah, I guess